6.5 Trapezoids and Kites. So the first thing we have to do is identify the parts of a trapezoid, that is, the trapezoids that are also not able to be classified as parallelograms. So when we talk about these specific trapezoids, the base or a base of a trapezoid is one of the parallel sides. So there's actually two bases in a trapezoid. Here they're labeled in the diagram. Then we have base angles. Those are angles that share a base. So there's two pairs of base angles. And then legs of a trapezoid, those are the non-parallel sides. So make sure you have labeled your diagram in your notes. One property of a trapezoid is that for an isosceles trapezoid, the base angles are congruent to each other. This doesn't mean that all four are congruent to each other. This just means that individual pairs of angles would have the same measure. So using that specific property of isosceles trapezoids, we can solve problems like we see in number 3. We're supposed to find the measure of angle A, the measure of angle C, and the measure of angle D. So the first one that we can find very easily is the measure of angle C, because angle B and angle C are base angles. They are a pair of base angles, and since this is an isosceles trapezoid, which we can tell by the markings showing the non-parallel sides, the legs are congruent, we know that the measure of angle B and the measure of angle C have to be the same, so therefore the measure of angle C is equal to 102 degrees. Now, finding the measure of angle A and the measure of angle D, there's not a specific property of a trapezoid for this, but we do know that since we have parallel lines and we can treat a leg of the trapezoid as a transversal, that we have same side interior angles. And we know from earlier this year, same side interior angles have to be supplementary since we have parallel lines. So we're able to find that the measure of angle A and the measure of angle D are both 78 degrees. Now, we do have an alternative way of finding this, and that is using the idea of a quadrilateral's angles adding up to 360 degrees. And we know that the two missing angles, the measure of angle A and the measure of angle D, are the same, so I've assigned them the same variable x. And then we just solve this equation using algebra. And again, we would find the measure of angle A and the measure of angle D both equal to 78. Here we have another problem that deals with trapezoids. So we have half a spiderweb being shown. They're formed by layers of congruent isosceles trapezoids after the innermost layer. Our job is to find the measures of the angles in ABCD, which is an isosceles trapezoid based on the information above. So the first thing we have to do is we have to actually look at our diagram and see that the first shape we would be dealing with would be this outlined blue triangle, which is an isosceles triangle. That's a key piece of information. So now, if we have an isosceles triangle, we need to find at least one of the angles to start, and we'd find the vertex angle by taking 180 degrees, since this is half, and if it were to go all the way around, it would be 360, but this is 180 degrees. This forms a straight line, the straight angle. There are 6 angles that all create that, and since all of these sections would be the same shape, we can say that each of these vertex angles of the isosceles trapezoid would be 30 degrees. You have to be able to find that. It's called a central angle to be able to start the problem. So now, using isosceles triangle theorem, we would be able to find we would be able to find the measure of the base angles of this isosceles the isosceles triangle. Since we know they have to be congruent, we can find the measure of one of them, in this case, the measure of angle CAB, by taking 180, subtracting the 30 from the vertex angle, and dividing that by 2. So we know these two base angles, CAB and ABD, would each have a measure of 75 degrees. Now that we know those values, we would be able to look at the specific isosceles trapezoid that I now have outlined in red. Since we know the measure of two base angles, we'd be able to find the measure of the other pair of base angles, similar to what we just did in the last problem. We know that a pair of angles that are not base angles and not opposite angles, so it's a pair of adjacent angles in this trapezoid, as long as they're not base angles, are supplementary by same side interior angles. So we'd be able to find that the measure of angle ACD and the measure of angle BCD are both 105 degrees. The next property of isosceles trapezoids is that the diagonals are congruent to each other. So this is a property that it has in common with rectangles. But now let's prove that this theorem is actually true. So here we have our isosceles trapezoid ABCD. We're told the legs are A and B, AB and DC, and those would be the congruent parts. So we start out with our given information, like always. And now if we're trying to prove that the diagonals are congruent, it would make sense to draw those diagonals into our diagram. So really, if you look at it, we've created triangles yet again, proving things about triangles, something we have a lot of experience with. So one thing I'd be able to say, and again, order can change here. You might think of this in a little different order than I have. We could say that angle B is congruent to angle C in this original trapezoid. So I could say angle B is congruent to angle C. Might not be a bad idea to name them angles ABC and DCB, just because of the added lines and angles now with the diagonals drawn in. But that I can say that because base angles of an isosceles trapezoid are congruent. That's a property of isosceles trapezoids we had just spoken about. Then we can see that segment BC is a shared side for the two triangles, ABC and DCB. So we can use reflexive property to say it's congruent to itself. Now we'd be able to say these two triangles are congruent using side angle side. And then finally, the diagonals, segment AC and segment BD, are congruent to each other by CPCTC. Moving on to kites now, diagonals of a kite are always going to be perpendicular to each other. So proof for this, instead of writing it out here, I've actually typed a paragraph proof for you. But before we get into talking about the paragraph proof, I want you to draw yourself a picture of this. Draw a kite, label it RSTW, and make sure you label it so that segment TS is congruent to segment TW and segment RS is congruent to segment RW. So here I've drawn a picture of the kite. Yours hopefully looks somewhat similar. So now this theorem, or this proof, says that both points T and R are equidistant from S and W. That comes from the congruent sides that we were given at the beginning of the proof. So then using the converse of the perpendicular bisector theorem, which we talked about last chapter, we can say that points T and R are both on the perpendicular bisector of segment SW. Since there's only one line through any 2 points from way in the beginning of the year, segment TR has to be the perpendicular bisector of segment SW, which then means they have to be perpendicular, and we have proven the theorem that says diagonals of a kite are always perpendicular. Notice in this theorem where it talks about having a perpendicular bisector, only one of the diagonals is bisected. Only SW is the diagonal that ends up being bisected. If both diagonals were bisected, we wouldn't be talking about a kite. What type of quadrilateral would we be talking about? Or, in other words, what other quadrilaterals have we discussed so far where both diagonals bisect each other? That would be parallelograms, both diagonals bisecting each other. Number 7 has us trying to find different angles within a kite. So make sure you add the 32 degrees for angle CBD. That's given information. So the easiest angle to find the measure of here, hopefully, is the measure of angle 1. The measure of angle 1 is automatically 90 degrees because we just talked about diagonals of a kite being perpendicular. So therefore, anytime we have a kite, which we're told we do here, the diagonal is perpendicular. Perpendicular lines always form right angles. All right angles equal 90 degrees. Then if I want to find the measure of angle 2, in this case, based on the information that I'm given, I can look at one of these small triangles within this kite, and I know 2 out of the 3 angles, and I'm finding the third one. So I add the 3 angles to be 180 degrees, and I can just solve from there to find the measure of angle 2 to be 58. And then lastly, measure of angle 3. Now this is going to come from the fact that if you look at this kite and notice how it's split into some different pairs of triangles, you actually can prove some of these triangles are congruent. In this case, I chose to look specifically at triangle ABD and triangle CBD. So the 2 largest triangles in the kite, they are congruent by side, 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 because segment BD is congruent to itself. So if we have the triangles being congruent, we can now say that we have the measure of angle 3 being 32 degrees just by using CP/CTC. So there we have our 3 missing angles. All right, now I'd like you to try some problems similar to ones that we've done together here. So number 8, here we have a piece of a ceiling that is shown made of congruent isosceles trapezoids. So imagine this goes all the way around. So it's a circular ceiling. There are 18 total pieces that meet at the center. What are the measures of the 2 sets of the base angles of the trapezoids? So what we're looking for are those values. I've labeled them X's and Y's. So your job now is to find those 2 values. To start this problem, we have to find what I referred to earlier as a central angle. That is done by taking 360, since I mentioned this is circular, it's going all the way around. We would take 360 and divide that by the 18 sections that we're told. So that gives us this entire angle in the middle being 20 degrees. Now, if you notice, you have the dashed line to only have half. So now we're dealing with 10 degrees within this shaded in portion of the picture. Now from there, we'd be able to find the values of X, because again, we can deal with this isosceles triangle. So X would be 85, those 2 base angles, both 85 degrees. And then Y, we would be able to use the idea that the adjacent angles of an isosceles trapezoid are supplementary by same side interior angles. So we'd have 95 degrees for those. So the measures of the two sets of base angles in this isosceles trapezoid, 85 degrees and 95 degrees. Lastly, in this kite in number 9, I'd like you to find the measure of angle 1, the measure of angle 2, and the measure of angle 3. So in this case, if I just go in order, and sometimes you can go in order, sometimes you can't, so you just have to be able to look at the picture, kind of think your way through. If you get stuck, maybe look at a different angle to try to find the measure of that one first, and then you maybe use that to help find a different angle. So the measure of angle 1, in this case, we have this kite, but we also have, if we look closely, an isosceles triangle. RSU is an isosceles triangle, so we know that this measure of angle 1 is going to be congruent or equal to the measure of angle RUS, which we're given as 72 degrees. So really, we already know that answer without really doing any work. We're just using the isosceles triangle theorem. The measure of angle 2 is 90 degrees. Again, don't have to show any work. We know the diagonals of a kite are perpendicular. So that's another one that we can answer just knowing some theorems and properties from earlier in this section. Now the measure of angle 3, this ends up being 18 degrees. There's a couple different ways you could go about doing this. You could look at one of the right triangles within the kite, figure out the measure of angle 3 that way. I chose to do it a little differently just to bring something back up for us. So in this case, I actually took 180 degrees, subtracted the two 72-degree angles, so I'm really looking at this isosceles triangle again, and then I divided that by 2, which gave me my 18 degrees. The reason I'm able to do that, you may remember from earlier in the year, the perpendicular bisector of the base of an isosceles triangle, so we know that segment RD is the perpendicular bisector of segment SU because of this being a full kite. We also can say then that that segment is a bisector of the vertex angle of that triangle.